All right. This time we're going to start talking a little bit about weather radar. So I'm going to pull my video so you actually can see it right here. Uh, we're talking about weather radio and talking about how precipitation forms. I thought I'd start with weather radio. I got the current WSR 88D image out of Albany, New York here. Actually Binghamton, excuse me. There's a line of thunderstorms right here. When a pulse of energy is sent out from the radar, what happens is is reflected back by precipitation, or even sometimes bugs or dust or other things in the air. The more it is, the intense the precipitation, the more reflection there is returned to the radar. So here is some very intense rainfall, and probably even some hail. Hail returns are very strong back to the radar. So these are kind of indicating that there's some very intense thunderstorms, probably even producing some hail. And you can see them down here as well, moving into this area. They've actually issued warnings. These are warnings for these thunderstorms. So let's take a look here and see if we can see a couple other things about this. Uh, Here is velocity. All right, velocity. Think about it when a train passes or a car passes you, you hear the sound change. And that's all that we're doing here. We're looking at the frequency change of that pulse of energy that we're sending out from the radar. Uh, right here, there are some pretty good winds. You'll notice here a scale is toward the radar and away from the radar. Well, right now we're going away from the radar, but we have some velocities in this range right here, 45, 50 knots of wind or more. So that says that there's probably 40 to 50, maybe even 60-mile-an-hour winds right along this line of thunderstorms. So with that, we're seeing that we have very strong winds we've just picked up. So these are all indications of a way we can use weather radar. Now, we have dual pole. I'm not showing you dual pole here. It would be kind of neat to look at possibly. I'm not sure I can get it to work very easily, but if I can, we'll take a peek at it. Uh, so let's see if we can get a product from it. There we go, hydrometeor classifications. All right, hydrometeor, what you can see with dual pole is you're getting a two-dimensional picture of a raindrop or some form of reflection that's back to the radar. So if I were to look in here, notice that I am seeing something that looks like this, GR, and maybe even a little bit more almost like hail into this area with the red. So what we're actually able to look at is, with looking at two dimensions, I can picture the size of the drop. Most raindrops are uniform, fairly small. Snow is very uniform. So you don't see a difference here. However, when you start seeing precipitation that begins to change, here's some heavier precipitation, bigger raindrops. But right here, I would argue there might even be some hail in this with the GR, maybe even moving into the red. So there's probably a hail shaft in that area. So we're actually able to pick that up with the radar in dual pole. That is one of the biggest pluses of dual pole. It can see precipitation types. Think about it. If you have a tornado, tornadoes tear apart buildings, put a bunch of debris in the atmosphere. Well, because of that, with dual pole, I can pick out that debris now. I'm seeing that in the air as well. So I can tell when a tornado is on the ground more often than not. With that being said, I'm able to tell you, oh, I have a tornado warning, and we're pretty sure we have tornadoes on the ground in this area. Makes a much stronger impact to somebody than me saying radar indicated a tornado, possible tornado. Now I'm able to tell you that there's pretty much certainty that we have a tornado on the ground. So that's what I wanted to show you with that a little bit. Let's just look at this a minute here. All right, we're going to talk about the clouds and precipitation now. I've talked about weather radar. So how do clouds and precipitation form? You'd say, oh, easy, right? Moisture condenses, there's a cloud. Well, no. Clouds actually require, for condensation to occur, a piece of dirt, something like salt or uh, erosion of soil, even things like domestic chimneys and exhaust pipes. Why is that? Well, raindrops are fairly big relative to a cloud droplet. Here would be an approximation of the size of a raindrop. Here's the approximation of a cloud droplet. Think about it. There's a very sharp curve here compared to the, longer curve. That sharp curve actually allows water vapor to escape. So that you actually need almost 300 to 400% relative humidity if you have completely no dirt in the air, very clean atmosphere. You're not going to get these. So by having a little bit of dirt, what that dirt does, it mixes in with that moisture and allows it to continue to stay together by the solution it creates. Now, as it grows, then it doesn't need that dirt, it gets less, so you get this big raindrop, but very little amount of dirt in it most of the times. And here you can see that. Now, if you have a flat surface, then you reach saturation at what we call it. But when you have that curved surface, water doesn't like to hang in there very well. It escapes back into a gas. So these little nuclei, and they can be dust in the Midwest, they can be salt along the coast. They're what causes it to happen, cloud condensation. Now, guess what? Water doesn't freeze when it's cold, when it's in the atmosphere as well. And that, again, these little circular balls of ice or whatever, water droplets in the atmosphere, just don't freeze. They literally have to go to about minus 30 some degrees Celsius in order to freeze. So, how do we get snow? Snow falls at 32, right? Many times. Well, what happens is there's ice forming nuclei, another form of debris, we'll say kind of like a dust or different chemical compositions. When they hit these nuclei, get in them, they cause them to freeze. So that is how we get ice forms. They actually inhibit, kinetic energy inhibits the growth of ice in these embryos. So it takes that, a lot of effort to get ice. Now, precipitation. Well, the bigger and bigger the droplet is, or the bigger the snowflake is, it has to get bigger before it will fall. Otherwise, air is going to resist it. There'll be friction, keeps it from falling. So there are two ways precipitation forms. Collision coalescence, that happens in warm clouds. Warm meaning basically the temperature is above 32 degrees. How it happens? Water just grows by a little tiny droplet, might get a little bit bigger than the other ones surrounding it. It falls a little bit, hits another droplet, until finally you get a rain droplet that falls all the way down to the ground. It's a very efficient process, but it doesn't happen a lot. It takes an awful lot of moisture in the air to cause this. Bergeron Findeis, and these guys were smart. Uh, they looked at cold clouds. They said, hey, clouds get cold when they get in the upper atmosphere. So what happens? Well, what happens is ice begins to form from these ice nuclei. And as they form, something unique happens, shall we say. The vapor pressure saturated for water droplets is higher than that for ice. Why is that? Well, the kinetic energy is higher in a water vapor. So what happens is the vapor the water vapor moves from the ice, from the water, excuse me, to the ice. So the ice continues to grow. So what happens is you wind up with a whole bunch of bigger and bigger snowflakes in the atmosphere, these ice crystals, and less water droplets with time. So the snowflakes grow bigger, they become big enough to fall. You wind up the beginnings of precipitation. Virga is just precipitation, that's evaporation before it hits the ground. So here are some types of precipitation: rain, drizzle, very small raindrops. And here are some types of snow. Notice, snow can look wildly different. Notice these dendrites, how big they are. If I'm forecasting snowfall at your house, I've got to make a choice on what type of snow I am going to have that falls. If I have dendrites, I might get 6 or 7 inches. If I have these thin plates or other types, I may only get 2 or 3. So I have got to understand as a forecaster what type of snowfall you're going to get. All right, so when you're at your house, say you're living there nicely and you've got a forecast of rain, what happens? Well, precip in the wintertime is going to start as snow. As it falls, it's going to reach air that's above freezing. It melts, it becomes raindrops. If it stays above freezing all the way to the ground, guess what? It's rain. Now, same thing happens. The rain comes in, it melts above freezing area, real near the ground, maybe the lowest 500 feet. Temperatures go below freezing, and then they can go pretty far below. I've seen freezing rain occur when the temperature was only 15 degrees outside. However, about 1,000 feet up, it was 32. So we had these rain all the way down, and all of a sudden, it's dropping into this teen air and freezing. So we get a sheet of ice. Now, if that air is a little thicker, they switch back into ice crystals like sleet. And finally, if they don't melt, they stay snow. So those are the different forecast issues. If I'm forecasting for your house, and you probably want to know whether it's going to snow or sleet, I've got to determine how thick this area is above freezing. And think about it, a warm front sends warm air aloft. So if I am on the cold side of that warm front, I've got to figure out how far in this warm layer gets and how thick it is as to know whether you're going to get which one of these. Well, here you just saw the freezing rain. We just talked about radar, and we've gone through a lot of that. Here's a typical radome, the Doppler effect we talked about. And here you can actually see a tornado on the ground with the radar showing the curvature, the circulation. We have a hook echo here, and we can see the radar right there. And I talked about the dual pole. Here is that debris signature. Here is where we can look at the weather radar also over the water and see a tornado. This is actually a hurricane coming ashore. Phased array radar. We're never going to see it in my lifetime, and probably not even in yours. It's expensive. They can use it in the military, but each one of these units costs about $1 billion. I've used it once out in Oklahoma City. It is tremendous at picking up tornadoes just as they're about to be forming, getting hail way aloft. I can give you almost 45-minute lead time with a tornado with this, but because of it, it's only so expensive, we just can't do that. So, and precipitation estimates, rainfall as well. Finally, we're going to talk about clouds a little bit, just the cirrus, high clouds, stratiform, and cumulus clouds. And here you can see the street. So I hope you got a little bit out of this. Let me know if you have any questions.